When it comes right down to it, nuclear energy is vital for the survival of life on Earth. It's the energy that powers the sun and gives us the heat and light we need to thrive. For billions of years, nuclear energy has been produced naturally in every star in the universe. Over the last century, humans have also learned how to generate it, creating some tough questions for society along the way. Nuclear energy gets its name because it involves the central part, or nucleus, of an atom. Scientists discovered that when changes happen to the structure of the nucleus, energy is released. There are two ways this can happen. The first is a process called fission. During fission, the nucleus of an atom splits into two or more parts. The total weight, or mass, of these parts is less than the weight of the original atom. Lost mass gets released as energy. In the other process known as fusion, energy is released when the nuclei of at least two atoms join together. This is how the sun gets its power. Scientists have found a way to create fusion reactions on Earth, and we now regularly use fission in several ways. We've built power plants that produce nuclear energy with machines called nuclear reactors. These reactors provide electricity for about 16% of the world. Nuclear energy is also used in medicine to help scientists diagnose and treat disease. But along with these advantages come dangers of staggering proportions. If nuclear reactions are not controlled, a tremendous amount of energy is released in the form of an explosion. These explosions produce radiation, which harms the cells of the body, causing sickness and even death. This is what happens with nuclear weapons, such as atomic and hydrogen bombs. If properly controlled, nuclear energy has the potential of becoming the most efficient type of energy in the world. Many people believe it will power us into the future when the Earth's other fuels become scarce. But some are concerned about the dangers and would like to see an end to all production of this kind of energy. It's a debate that is sure to continue well into the 21st century. Ever wonder why stars are so bright, or how the sun produces so much heat and light? It turns out each star is a giant nuclear furnace that releases energy at its core. It's nuclear energy that lights up the sky. The sun is the star that glows closest to the Earth. It gets its energy by burning gases at its core in a process called fusion. Like most stars, the sun consists almost entirely of two gases, hydrogen and helium. During fusion, hydrogen atoms collide with such strong force that they fuse together to make helium. Each second, 600 million tons of hydrogen convert into 596 million tons of helium. The missing 4 million tons of matter are transformed into energy. This process is only possible because of the enormous heat and pressure found at the center of the sun. It's about 25 million degrees Fahrenheit in there. Energy moves from the center to the surface of the sun with dramatic results. The most spectacular sight is an enormous explosion of energy known as a solar flare. These flares send radioactive particles into space. Particles that get carried by solar winds. They reach the Earth in a day or two, where they're deflected by the Earth's magnetic field. But at the North and South poles, these particles can hit the Earth's atmosphere and produce brilliant light shows known as auroras. While not everyone has a chance to see an aurora, all of us certainly experience the sun's energy each day. At 93 million miles away, we are far enough removed from this star to enjoy the benefits of its heat and light. During photosynthesis, plants collect energy from the sun's light and use it to make food. Like every star, someday the sun will run out of the gases that fuel it and gradually fade away. Astronomers believe the sun is more than 4 billion years old and has already burnt up about half of the hydrogen at its core. But no need to worry. It still has about 5 billion more years to go. The nuclear energy that powers every star seems almost inexhaustible, and for that reason, scientists would like to find a way to generate it on Earth. But that's a tall order. It requires them to duplicate and control the same conditions found at the center of the sun. Scientists are working on ways to do just that. One of the most important applications of nuclear energy is in the field of medicine. In nuclear medicine, small amounts of radioactive materials are used to help doctors look at the inside of the body and treat disease. The procedures are safe and non-invasive, and they allow doctors to gather information that might otherwise be unavailable. Nuclear medicine had its start in France in 1902, when scientists Marie and Pierre Curie made a critical discovery. While conducting research on radioactive substances, they found that one substance gave off more radioactivity than others. They determined that the source of this radioactivity was two elements, radium and polonium. Monique Baudry, curator of the Curie Museum in Paris, notes,
their work was extremely important. The discovery of radium opened up a whole new era. It's been described as the nuclear age. Pierre and Marie were the start of modern physics.
Their daughter, Irène Joliot-Curie, took their findings even further by developing artificial radiation. She found that by bombarding aluminum with naturally radioactive particles, the aluminum itself became radioactive. When particle bombardment ceased, the creation of radioactivity continued. This artificial radioactivity quickly became useful in medicine, and it's still used today to diagnose and treat disease. Dr. Ian Fraser explains.
Radiation therapy is a localized treatment of cancer involving external beam radiation and insertion of radioactive materials into the tumor. Radiation therapy was actually in use within a year of the discovery of radiation. Since then, it had become a highly sophisticated treatment of cancer. Of all cancers, radiation is the second most used after surgery.
At the time of the Curie's discoveries, the harmful effects of prolonged exposure to radiation were not understood. As seen in this photograph, handling radium produced scarring on Marie Curie's hands. Even worse, repeated contact brought on the cancer leukemia. Both she and Irène died of leukemia before the age of 70. The Curies dedicated their lives to science, and their discoveries continue to prolong life today. During World War II, the nuclear age literally exploded. It was a time when an overwhelming fear of Adolf Hitler and his Nazi regime was at its height. A deep mistrust between the United States and Soviet Union also began. The result was a race to build a weapon capable of destruction unlike anything seen before. By World War II, physicists knew about the power of nuclear energy. Driven by intellectual discoveries, they had worked for years to unravel the mysteries of atoms. Eventually, they discovered that splitting atoms of the elements uranium and plutonium released an enormous amount of energy. Energy that could create a massive explosion. They used this discovery to create a bomb. In June of 1945, the United States had built and tested the first atomic bomb. Less than 2 months later, the U.S. used this weapon against another World War II enemy, Japan. In an effort to put a quick end to the war, 2 bombs were dropped on the Japanese cities of Hiroshima and Nagasaki. Over 200,000 people were killed by the explosions and the radiation released. The effects of the bombs were so alarming that nuclear weapons have been a subject of political debate ever since. The atomic bomb is sometimes called a fission bomb because it operates by uncontrolled nuclear fission. When the nucleus of a uranium atom splits, particles fly out with such force that they split other atoms. A chain reaction begins. If it's not controlled, the result is a powerful explosion that happens within a fraction of a second. But 1,000 times more destructive than the atomic bomb was the hydrogen bomb first tested in 1952.
The Pacific is the chosen proving ground for the United States H-bomb experiment, here amid vast ocean spaces far from human habitation.
This is the first full-scale test of a hydrogen device. If the reaction goes, we're in the thermonuclear era.
8, 7, 6, 5, 4, 3, 2, 1.
Unlike atomic bombs, hydrogen bombs use a fusion reaction in order to explode. The same reaction that powers the sun. Nuclear weapons have not been detonated in war since the first bombs were dropped in Japan. But many countries now possess them. Some argue that all nuclear weapons should be disposed of. Others want to establish international treaties to make sure they are never used again. They can operate underwater at high speeds for months at a time. And they don't make a sound. Nuclear-powered submarines are the most advanced and lethal of all naval warships. Inside their steel walls, these ships hold powerful weapons such as missiles that can reach targets thousands of miles away. But as Navy Commanding Officer David Volanino notes, the goal is not to use them.
The mission of America's ballistic missile submarine force has always been deterrence of war. It is a very necessary thing for us to maintain a strong nuclear deterrent force so that any country that possesses nuclear weapons or other weapons of mass destruction will never consider using them against America or her allies.
These subs are powered by nuclear reactors that generate energy through fission. Inside the reactor core, the fission of uranium fuel produces an enormous amount of heat. This heat is carried through the system and used to boil water into steam. The steam is then used to power the submarine by generating electricity. It's an efficient system. It only takes 4 pounds of uranium to yield the same power as 10 million gallons of fuel used by the early diesel-powered subs. And it solved a big problem for the Navy. Before nuclear power, submarines were vulnerable to attack because they had to resurface and refuel more frequently. Building a nuclear sub was the dream of Navy Admiral Hyman Rickover. He was the first to realize that nuclear power could vastly improve these underwater machines.
A qualified submariner and engineer with a strong faith in both the practicality and necessity of atomic propulsion. His convictions and determination soon made him a dedicated and efficient spokesman for a nuclear navy.
Figuring out how to control a powerful atomic reaction on a submarine was quite a task. But in 1955, Rickover's dream was realized with the launch of the USS Nautilus, the world's first nuclear-powered sub.
Underway on nuclear power. That was the terse message that sent the Nautilus and her crew into service.
Today, more than 20 nuclear submarines continue to patrol the world's oceans, often undetected.